In the same way that the refractive index depends on frequency within insulators, we also have the same behaviour in metals, this idea of dispersion. We can think of the metal as being consisting of two classes of oscillator. The bound electrons which hold the material together, and the free electrons. And so this is an assembly of driven damped oscillators, and some of the free electrons, some of these are free electrons and they don't have any restoring forces, they don't have any natural frequencies and so on. Others are bound to the atoms and they look and behave very much like they did in the description of dispersion in dielectrics or insulators. For metals, the conduction electrons are the dominant effect. They are the biggest influence on the optical properties of the metal. For the free electrons, if we apply an electric field to the electron with a charge of Q and a mass M, then the displacement that's produced will be given by the expression here. Okay. No restoring force means that the omega naught is 0, and so we can see that the sign here, this negative sign, will come out, and we have that the displacement is in the opposite sense from the direction of the electric field. So displacement is an opposite sign to the driving force. In other words, the electrons oscillate 180 degrees out of phase with the driving frequency for normal frequencies. These free electrons, if we oscillate them and drive them backwards and forwards, they radiate their own waves. So this oscillating electron will produce its own electric field, its own little kind of wavelets. And because they're out of phase, then they'll tend to cancel the incoming light. Two waves added together, which are out of phase, will tend to cancel each other. And the result of this is that the transmitted ray, the refracted ray, is very rapidly decaying. That's what we've seen above. The dispersion equation for metals, we can extend the model that we had already for the insulators, where we have this expression here, the sum over all the electrons, the bound electrons, which depends, and that expression depends on the resonance frequencies, the driving frequency, and the damping term. And for the free electrons, then obviously we have no resonance frequencies, but we have the driving frequency and we also have a damping term. So this extra term here comes from the free electrons. And N at the start here is just the number of atoms per unit volume. So if each atom has Fe conduction electrons and they have no natural frequencies, then they will be oscillating, as I say, out of phase with the incoming electric field. The behaviour of the bound electrons, whether they're in phase or out of phase, will depend on the frequency. It depends on the driving frequency. So that second term for the bound electrons is exactly the same as the one we had for dielectrics, for insulators. And so that will give us a kind of basic understanding of what's happening at that level. But as I say, the free electrons are the ones which dominate. An important point to note here then is that if a metal has a particular colour, then it's mostly due to the way in which it reflects light. So if a metal has a particular colour, it's not because it absorbs light. So if I think about maybe a window, a stained glass window, and it has blue glass, then what's happening there is that all the other wavelengths are being absorbed by the glass as the light travels through it, and only the blue light can get transmitted through, and that's why it looks blue. For metals, if we have a bluish finish on a metal, then that's because it reflects the blue light much more strongly than the red and the green, the yellow, and so on. So there are important differences between the behaviours of insulators and metals, and one of them is the mechanisms which give it its colour. So for insulators, it's a transmission process. The light which passes through is allowed through, and it gives it its colour. So and the other colours will be blocked. So if it's a red piece of glass, then the blues and the yellows and the greens will all be blocked. Whereas if it's a piece of metal, if it's a red piece of metal or something like copper, then it's because it selectively reflects those wavelengths. So gold and copper, reddish yellow, because the reflectivity increases with the wavelength. So the longer wavelengths get reflected more, and that's because the complex part of the refractive index increases with wavelength. So these materials are opaque at longer wavelengths, but if we go to short enough wavelengths, then they will become transparent. For a CO2 laser, gold and usually copper, which is coated with gold, are two materials which are often used for making mirrors, because you want them to be highly reflecting. So this is just a diagram which shows you for the bound electrons. So this is our input driving force. So our force is just equal to the charge on the electron times the electric field, and it's oscillating here in a sinusoidal way. For the bound electrons, if the driving frequency is much less than the resonance frequency, the natural frequency, then you'll see that the bound electrons oscillate in phase. If the driving frequency is about the same as the natural frequency, then they oscillate 90 degrees out of phase. And when we have our driving frequency much bigger than the natural frequency, then they're 180 degrees out of phase. So you start getting that cancellation effect. For free electrons, for all frequencies, they're always 180 degrees out of phase.